Good morning, students. This is Dr. Eustace Russell, working as assistant professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So far, we are seeing the subject called Kinematics and Dynamics of Machinery. The subject code of MR3451 with the regulation of 2021 for the 4th semester. Second year students studying this paper. Last slide we have seen that Unit 4, some introduction part we have covered so far, basics that we have covered so far, that is applied forces, constraint forces, and how these forces are happening, and what is the necessity of these forces, what are the various examples we have seen so far, and followed by the basic free body diagram, what is the necessity of the free body diagram also we have discussed so far. Today we are going to see that the upcoming topics in the force analysis we will see one by one. So in this free body diagram, static equilibrium condition for the 2, 3 and 4 members also they are mentioned in the syllabus. So before going on to that, we must know that what is static equilibrium conditions. This every equilibrium conditions we have studied in engineering mechanics subject in last semester. Now what is static equilibrium means? The body is in static equilibrium if it remains in its state of rest or motion. If the body is at rest, it tends to remain at rest, and if in motion, it tends to keep the motion. So you can understand one thing, if it is in the state of rest, then it will be under state of rest only, that is under static equilibrium. So dynamic equilibrium is nothing but if the body is in motion, it tends to keep in motion. It's simply that the velocity do exit but remain constant, that system is in dynamic equilibrium. That two difference is there. So the first thing is static equilibrium. Second, dynamic means you have to consider the motion. These are the various conditions that is given. That is sigma f equal to 0, sigma t equal to 0, sigma fx is equal to 0, sigma fy equal to 0, and sigma tz is equal to 0. That is sometimes we have to take the moment also, that will be considered. The forces as well as summation of moment about that point will be equal to 0. Now the equilibrium of 2, 3, 4 system, that is the members we are going to see one by one. A member under the action of two forces will be in equilibrium if the forces are of the same magnitude, the forces act along the same line, the forces are in opposite directions. So we can see here there is a principle of transferability. Here it is clearly mentioned. One object or one particle is there. One of the forces acting in one direction, that is, let it will be F1, and another one that is forces that is acting in the same direction but in opposite direction, same path but in opposite direction, that is F2. Direction only it is differs, but magnitude is same only. Therefore F1 equal to F2. A member under the action of three forces will be in equilibrium if the condition is that resultant of the forces is 0 and the line of action of the forces intersect at a point that is known as point of that is congruency. That is under the acting at one point, that is called concurrent forces. Already we have seen in the mechanics. Here this is one particle that is acting also, it is mentioned in the sketch. Now static equilibrium condition, that is continuation, we can see equilibrium of 2, 3 force members. The first figure we can see that figure A shows a member acted upon by three forces. Here we can see what are the forces, how many forces are there means we can see in the figure name, that is A, figure A. You can see that F1, F2, F3, it is acting on one particular point. As a line of action of forces intersect at one common point, that is O, and the resultant is 0. This is verified by adding the forces vectorially. That is sketch B. We can see that. So we can see that F2 is going downwards. The B figure it is mentioned. F1, that is again moving in the downward direction. We can see that. Then the closing polygon will be F3. That is figure number B. Figure D shows a case where the magnitudes and the direction of the force are the same as before, but the line of action of the forces do not intersect at one point. Then that member will not, we can't say that is under equilibrium. It will not under equilibrium. That is, the member is not in equilibrium. That is the main case, because F3 is not acting in one point. It is away from the point O. So it is not in equilibrium condition. Here we can see this. Again, the continuation part of this one. Consider a member in equilibrium in which force F1 is completely known, F2 known in direction only, and F3 completely unknown condition. Okay, the point of application F1, F2, F3, or we can consider as A, B and C. We are giving one name, that is A, B, C. For solving this type of problem, first find the point of concurrency, that is concurrent point O, from the two forces with known directions. Known direction means, what are the known directions? We can easily tell that F1 and F2. Joining O with C gives, what it will give? The line of action of the third force, that is F3. To know the magnitude of the forces F2 and F3, take the vector of proper magnitude and direction to represent the force F1. From these two ends, draw the line parallel to the line of action of the forces F2 and F3, forming the force triangle. This is the polygon. By using the instrument, you have to draw the closing polygon line. Make arrowheads on F2, F3 so that F1, F2 and F3 are in the same order. We can see one slider crank mechanism, it is given in the figure. One crank is there, that is O2 fixed to the crank. Crank is fixed to the point O2. That will have a rotary action. And the link 3, that is a connecting rod connected with a slider mechanism that is shown in figure. That is the friction force with static force analysis we can see in this figure. And lower that diagram also, the various forces that is acting in the system, that is shown clearly. So an object is in equilibrium when there is no net force acting on an object. There is no net torque. In other words, the object is not experiencing linear acceleration or rotational acceleration. We can easily understand that. So when an object is in equilibrium, there is no net force acting on an object. There is no net torque. It is not experience any linear action, linear acceleration or rotational acceleration. That is A equal to del V by del T equal to 0. And angular acceleration will be given by, that is change in displacement, change in angular displacement with respect to time, which is equal to 0. That is del omega by del T equal to 0. Here various real-time application here it is mentioned. Here we can see that in the above cases we can see that member AB can consider as a two force members, provided that their weight is neglected. This fact simplifies the equilibrium analysis of some rigid bodies, since the directions of the resultant forces at A and B are thus known along the line joining points A and B. Here we can see in the slide in the left hand side sketch, that is you can see there is a crane or JCB machine also we can see in the day-to-day life for pulling any concrete or sand or any hard materials. We can using this type of machinery equipments, and that we can see the links, that is AB member that is mentioned over here. There is a two force members. Equilibrium analysis can be done for these rigid bodies. And on the right hand side also we can see that AB, one shock observer that is mentioned over here, one suspension type it is given AB, that is the equilibrium that is given over those rigid bodies, and we can have a study analysis on these members. So by using these references, I prepared the content for these topics. So kindly go through these references for your understanding purpose. So kindly go through the video. I think this will be useful for you. Today we have seen the various equilibrium conditions for 2, 3, force members. So please subscribe the channel. Please share this video to your friends. In upcoming videos, you will see the remaining topics in force analysis. So thank you one and all.